I'm going to talk about the migration of the eMolecules database. How many here have never seen eMolecules? Nobody? Cool. There's one. So I don't have to go into a lot of detail to explain. I do have a few slides here that I'll talk about. There we go. Let me just tell you briefly then what we do, since most everybody seems to be familiar with it. We are in the business of connecting buyers of chemicals, research chemicals, with the suppliers of research chemicals. And in order to do that, we have a chemical search engine and an e-commerce system that we use. We have 10 million products in our database. About 2 million of those are building block compounds, 8 million are screening compounds. We also recently went into the antibodies business. We have about 600,000 antibodies in our database right now. I'm not going to talk about those at all. Among the things we do to make this a good buying experience for you is primarily our focus is on quality data, comprehensive, up-to-date quality data. We have really good relationships with the suppliers. We have supplier associates who are in contact with the suppliers daily, weekly, monthly. We have fast catalog updates, sometimes as frequently as every day for things about like availability. Data normalization and cleanup is a really critical part of what we do because we get a lot of junk. I mean, people have talked about that several times today. You'd be amazed the stuff. I mean, the people who are making chemicals and antibodies they're chemists. They're not cheminformaticians, and they don't really understand what it means to put together an electronic document that makes sense. Some of them are very good, but some of them aren't. So we do a lot of data normalization, curation, QA, that kind of stuff. And perhaps the most important service we provide is because we place hundreds of orders per day with hundreds of suppliers, we actually know how good they are. And if they say they deliver in 1 to 3 days and they don't, then we know that. And so we have a series of tiers, tier 1 through 5, where tier 1 means they ship in 1 to 3 business days, tier 2 means 5 business days, and so forth. And if a supplier doesn't deliver, we bump them down, and it's a big deal to that supplier. So being one of the biggest actual procurement companies in the world, we can do that. So how do you go about ordering chemicals? The first thing you have to do is be able to search. By substructure, similarity, exact structures, the traditional cheminformatics system. I was thinking today, this may be about the last homegrown cheminformatics system in the world. Because of companies like ChemAxon. It used to be a lot of companies, pharma companies and so forth, would build their own, and when we started eMolecules, it was the right thing to do because I could work 15 hours a day and I knew how to do it, and it's cheaper than buying ChemAxon at the time. So in addition to the raw searches, you're also able to refine, browse, filter your data, sort your data, that sort of thing. And of course, collaborate by importing and exporting hit lists. This is a screen you'd get if you went to www.eMolecules.com and just entered a search. You'll see at the top here we have, at the top of the columns, we have various, you can't quite read those, but we have our system based on a hit list, which I'll talk about a little bit more. But when you do a search, we have 2 different searches. And a lot of people don't even realize this when they come to eMolecules. But when you just draw something, it does a very lightweight, fast search that just returns 10 rows to you, and then it forgets who you are. And when you come back for the next page, it doesn't start over again, but it doesn't redo the search. It starts from where it left off, and I'll explain that in a few minutes. This is a really critical thing for a website. And then if you want to do a more sophisticated search, you'll click on Work with this list, and it does a full hit list search. And then you can do filtering and sorting and all of the other things that all of the informatics systems we've seen today find useful. Then when you've got your list, you can add stuff to your shopping cart. Here you can see our tiers. Tier 1 ships in 1 to 5 business days. It gives you the prices, who sells that, package sizes, and so forth. And you fill up your shopping cart and you order it, and we see to it that it gets to you. As I said before, we try to stay super accurate, up-to-date, accurate lead times, curated data, and we monitor suppliers' delivery times on a daily basis. Another thing that a lot of you may not know is we operate over 100 private websites for all of our pharma and biotech companies. This is one, Heisenberg Pharma. This is a test one. I did this before Breaking Bad came out. I just thought it was a funny name. So it has nothing to do with that. But the idea is that a customer can have their own skin. We do a little bit of customization on the front end here. But more importantly, we customize what catalogs are in there. So if they like 10 preferred building block suppliers or screening compound, whatever, we customize that for them, that content, and then that ensures that they get the compounds that they want from the suppliers that they like. And also, a very important thing is that we provide security, access restrictions, verified logins, IP address restrictions, that sort of thing, so that you can be sure that nobody else can get into your website, your ordering system. And finally, we do partnering. Jaeger was going to be here, but they couldn't, so they asked me to stick in this slide. We have web services that allow our partners to present eMolecule structures and searches into their systems. So in this case, Jaeger, which is the former, I think that's how it's pronounced, I'm sorry if I get it wrong, former SciQuest, their enterprise reagent manager, they federate their inventory searches with us with eMolecules so that it simplifies their customers' inventory management system. So let's get into the meat of the matter, which is cheminformatics. That's why we're here. The engine that I'm going to briefly describe, the search engine that we have now that we're about to replace with the ChemAxon system, because it's relevant to what we had to do in order to get ChemAxon to work for us. And I should say that the work that Andreas is doing is pretty cool. It may make some of what I'm about to tell you obsolete in the not too distant future, which is good, which is one of the reasons we're partnering with them. So our current system is fast. Most queries return in 1/10 of a second to 2 seconds. And this is a critical thing. It's stateless. That is, when you do a query and it gives you those 10 pages, it forgets who you are, that you were ever there. It's just gone. It's got your answer, and it's done. So each subsequent query, page 2, page 3, page 4, is a completely new query. And it can start where it left off, and I'll explain how that works in a minute. So it's super efficient. It's, if you say, give me rows 1 through 10, which is page 1, and stop, it stops when it gets to the 10th row. And then when you say, get me page 11, it starts exactly where it left off before, and then it goes without redoing page 1. And that's one of the flaws in relational databases. They're not very good at that. We also have these hit lists I talked about a minute ago, power searching. One of the problems with websites is that places like Google and Bing and so forth, they've led to user expectations. So when you go to Google, if you type in, you know, find me everything about Britney Spears, it tells you like that. I mean, you get an answer. And people, you know, cheminformatics is actually harder than that. And for really good reasons, theoretical, graph theory, mathematical reasons. You can't just do that with cheminformatics. And the problem is that people don't care why you can't give them an answer quickly. They just think you're not very good at what you do if you don't give them an answer quickly. And so you have to give them an answer quickly. And so there's a couple, but sometimes you can't. And so what you need to do in that case, you know, certain chemical queries, especially if you combine them with other things, can take 10 seconds, 20 seconds, a minute. And depending on your cheminformatics engine, even more. And so you can't just have the thing there spinning and spinning because people will go, what's going on here? And they hit refresh. Now you got 2 queries going on, you know, and so forth. So you need to have, number 1, immediate feedback saying, I'm running your search. And then number 2, how am I doing? And so you have a little progress bar that tells you, and it has to be right. And another important thing is to have an interrupt cancel feature, because if somebody launches a query and it says it's going to be 5 minutes, they say, well, I probably didn't want to do that. Let me see if I can be more specific here. And you give them a chance to cancel the search and then try again, whatever it is they want to do. Another thing we allow is multiple stored hit lists and hit list operations. That is, you can do one search. Let's say you want to find everything that has a 5 or a 6-membered ring. Which is hard to do with languages like smarts and molecule editors and things like that. You can do the first search for the 5-membered ring and then the same search for the 6-membered ring, and then you combine them. You can merge your results into one. So you don't have to think up these complicated queries in your head or write these ridiculous smarts or whatever it is you have to do. Hit lists are great for that. We also have a feature that is not exposed currently, but I probably will at some point in the not too distant future, where you can do all kinds of like subtracting and difference and intersection operations on these hit lists, which allows you to do some incredibly powerful searches without having to do a lot of thinking in your head about how these, you know, how to construct this query. So why are we replacing eMolecules' homegrown system? I mean, obviously it's cheaper for us, or at least it used to be, to do our own than to buy products. Well, the reason is because in the since 12 years, since 2005 when Klaus and I started eMolecules, first of all, we've become a real company, and the commercial products are just better. The problem is, you know, I'm the cheminformatics guy at eMolecules, and I can't compete with a bunch of Hungarian programmers. So, I mean, that's what they do for a living. And It's very much like the reason that eMolecules itself is in business. And we have a thing that we do. We connect suppliers and customers, and we provide all the logistics in between. We provide quality data. What we don't do, we're not in the business of doing good at cheminformatics, but these guys are. And so we should partner with them rather than trying to do it ourselves, and then we can focus on the things that we do well and get on with that. The second thing that happened was that it became available as a Postgres cartridge. We use Postgres under the covers to do all of our work, and so that was important for us. We find that Oracle's licensing model is not acceptable. And then thirdly, the cost of maintaining compatibility with the open. We use the OpenBabel, which is an open source cheminformatics platform or toolkit, and it's just hard to keep up with it. You know, as they make changes, they have different people who are working on it and so forth. It was a lot of work, and so this is a better solution to go with ChemAxon. So now let's talk about the web in a little bit more detail. The problem with working with the web with any kind of database system is that the web is kind of your friend and your enemy. So you have these lightweight, stateless, fast queries that people do, and you just don't know who's going to come up to your website. A lot of you people are talking about, you know, your customers are pharma companies, and they don't do stupid things, and if they do, you can go and say, hey, knock it off. When you have a public website, you can't do that. You just don't know who's going to come to your website. So you get a lot of guest users who have no stake in the result. They're just there. They're college students. They're, you know, Hayo was telling me that we got an order from some high school the other day. And who knows, it was like a morphine precursor or something. Like, we're not going to ship to you guys. I'm sorry. You just don't know what's going to come in. And you also, perhaps more significantly, you have abusive robots. They just like try to steal everything. The biggest single problem we have is industrial theft. So we get queries all the time from what appear to be CROs in India and China. They have some research program they want to do, and they want to buy a bunch of stuff, and they don't want to pay us to do it, so they set robots on our site. We once had an attack, probably state-sponsored from China, of over 10,000 servers trying to withdraw data from our database. It was pretty hard to stop. So these are the kind of problems, and these all can involve substructure searches. So these are the kind of problems you face on a real website that's public-facing. So you combine that background with what does a relational database do well and what does it not do well? First of all, you almost never get instantaneous results like Google and Bing. In fact, Google and Bing don't use relational databases for that very reason. They have their own homegrown databases that are very good at what they do. Sometimes queries can take minutes, even longer. They have poor pagination. Relational databases are not designed to do pagination. They have ways of doing it, but it doesn't work very well. And they don't have any way of telling you how far along. You issue a query, when it gets done, it's done. In the meantime, you have no idea how the query is going. And it's hard, but not impossible, to interrupt or cancel a search. And the result is, if you just went with a straight database query, issued the query that the user wanted, and waited, it would be a poor web experience, and everybody would think you weren't very good at what you did. So let's go through some of the technical reasons why that is. I'll go over this fairly quickly. This pointer, I don't know if you can see it, but this is a simple query that relational databases do really well. And I'm illustrating this first to illustrate why they don't do some other things well. So we're asking, does eNamine sell this cast number? We do a query here. It's going to look for a cast number and a supplier ID. It turns out it has indexes on both of those. It estimates that it's going to come out with 178 cast numbers, 20,000 eNamine compounds. It takes the intersection of those two, finds one compound in 13 milliseconds. Great. That's wonderful. That's exactly what you'd like this thing to do. Now let's look, so relational databases handle this really well, and the reason is because the statistics that they can develop on each column in the database are really good. And that means within an order of magnitude or so. And good predictions lead to good execution plans in the SQL. This does not work for chemical queries. And the reason is because, for theoretical reasons, the statistics on chemical columns can't be as good as the statistics on number and text columns and things like that. And poor predictions lead to poor execution plans. So let's do a couple of queries. The first one is a stupid query. And it's probably the most common single query we ever get on eMolecules. And I'm not kidding. I mean, just, you know, some high school kid comes along, oh, what's this? Click, click, you know. Nico was telling me the other day that his daughter had got a hold of his phone, and she was in benzene search, benzene. So, and then we have a selective query that out of our 2 million compounds has exactly 3 hits. This is a real thing that somebody might actually look for. So, and here's the critical part. We want the first page of results. We don't want all the results, and you'll see why that's so important here. So here's our query plan for the good query. And over here you'll see that this, I won't bore you with all the technical details, but it works from the inside out. It does this first, then it does this, then it does this. So it estimates that the time this is going to take is between 100 milliseconds and 60 seconds. Now think about that for a second. This is what Postgres, and by the way, I have to emphasize, this is not ChemAxon's fault. This is just the way relational databases work. The fact that they've integrated their system within Postgres means they have to deal with the limitations of Postgres. Postgres can't tell how long this is going to take. In fact, that's correct. That is about the range of things that it would take for a column like this. The actual time is 177 milliseconds. It returns 3 rows, and it does this other thing. We have a limit 10. This is the critical thing here at the end of this, is this limit 10. That's the thing that's going to screw us up in the next query. So, and there's only 3, so it doesn't have any limit to apply, and it's done 173 milliseconds. We're pretty happy about this. Now look at this one. Interestingly enough, it's the exact same plan. In other words, it couldn't tell the difference between those 2 queries when it was doing the SQL plan. So this time, instead of taking 700 milliseconds, it takes 24 seconds, and it comes back with 1.3 million rows. What does it do then? It throws out all but the first 10 of them. This is not an optimal plan. And I know what's going to happen is that, you know, Andreas here is going to say, I can fix that. Or he may have already, and he probably can. But the problem with relational databases is that every time there's a software release, or every time your database grows, the query plans, the SQL plans can query. This is, if you follow the, you know, the way down deep news groups and stuff that SQL guys do, they're full of complaints. My website was working and now it's dead. And what happened was their database grew beyond some threshold. The query planner picked the wrong plan after that. They have to go in and restructure their SQL. It's just a nightmare. You don't want to do that. You can't operate a website reliably like that. So you have to find a different solution. So I'm just getting ahead of myself on my slides here. I just said this stuff. Optimizer predictions are not good for chemistry. The query times are variable. And even if you give hints, restructure your SQL, that sort of thing, it still might get it wrong in the future. There's no way to run a website. So how did our current system handle this? Well, this is just a very broad architecture of the thing. We have at the top all the different queries that might come in. You have names and cast numbers and MFCDs and structures. And we look, the main application looks at the query and says, is this a chemical query? If it is, it sends it over to the eMolecules search engine. That's the one we're using now. If it's not, it does the query directly in Postgres. If it is a chemical one, it finds the answers and it sends those to the Postgres database. So it's, and the reason that this is so cool is that the eMolecules chemical database is not a general purpose search engine. And why is that important? Well, the problem with Postgres and other relational databases is that they have to be able to answer any SQL, and there's some very complicated SQL in the world that might get thrown at them. So they have these really complicated planners and all this stuff. If you know what query you're going to get asked, you can always do better than a relational database if you write it by hand. In this case, there's exactly one query. Find this molecule, either as an exact or similarity or substructure. And so I could write that thing to do that really, really well, and I did. So, but another thing that's really, there's a little detail here. One of the cool things we were able to do is dynamic optimization, which is as the query goes forward, it can actually look at how well it's doing and change the query plan dynamically. Relational databases can't do that. But the most important thing we did was this execution state. So after you do the first row and you get to row 10, with just a few bytes of data, it could encode those few bytes and send them back to the user's browser. And then when the user said, I want page 2, it would send those bytes back and we could restore the search engine to exactly where it was when it left on, and then we could do page 2. And so that allows us to not have to do reissue the query every time. So it was extremely efficient. So that doesn't work. If we want to use the ChemAxon cartridge, that doesn't work. We have to come up with entirely new solutions. Well, fortunately, Postgres has this really cool thing where you can partition tables. So if we have 10 million compounds, instead of putting it in one big table, we can put it in 20 partitions. And the cool thing about that is that you can, you can query either the full table and Postgres just takes care of it for you as though it were one table, or you can query each partition individually. So now instead of having 10 million compounds, you have 500,000 compounds in each partition. So what you do when the user comes along and gives you the stupid query, which is benzene, is you say, okay, I'll put that in the first partition. And instead of having a 24-second response time, you have sub-second response time. And if you get the 10 rows that you want, you stop. And in fact, the query is still done fairly inefficiently because it's still going to take, well, you got 500,000, it's roughly half the structure, so it brings back 250,000 structures. You limit it to the first 10, but it takes less than a second, so who cares? So that and the second thing it does is that it allows you to give progress reports to the user. So as you're going along, since you're actually querying each table, I can say I have 5% done, 10% done, 15, 20, and the user says cancel, you can cancel it, all that good stuff. So using Postgres' built-in partitioning mechanism solves that problem, several other problems too. So it gives you the fast response time for dumb queries, and it gives you the progress reports, and it gives you the ability to cancel in the middle of a search after you know, and you can sort of see how well you're doing. So how well do we do? Well, the benzene query, the first 10 rows from 1.3 million hits, the full search took us 28 seconds. The search of 5% is less than 1 second. It's about a 30-time speed up. It's a little bit faster than 20 to 1. Databases tend to do that. They scale by n log n sometimes, or maybe it was just a particular partition, I don't know. But then you might say, well, what about the selective query? You know, it's going to return 3 hits, 17 of the partitions it queries, it's not going to find anything. You know, did we waste a bunch of time here? What's worse than that is that it actually has to replan the query for each one of those. So it's going to do an SQL query, it's going to do the plan, it's going to execute the plan, it's going to give you the results. How bad is that? Well, it turns out the 2 million compounds, it took 85 milliseconds to do this query, which is amazing. When we search 2 million compounds in 20 parts, it takes 128 milliseconds, which is a 43 milliseconds slowdown. Who cares? This is amazing. So it works out really well to partition tables this way. So I think I'm getting ahead of myself, but the progress report, this gives us progress reports during the search via partitioning. We have our hit lists store the results persistently, and also allows us to do fast perusal of results. When we get through, you've got a hit list, and you can go, if it's like 10,000 hits, you can go to the last page, first place. It's not doing any further searching because you've already got your results stored in a hit list. And it says here a demo. I think I'm going to go over time if I try to do that. I don't know that we have a browser available anyway, but I would invite you to check out eMolecules.com just for today only. If you like, I've opened up, if you go to ChemAxon-demo.eMolecules.com, it doesn't do the fast search, it only does the hit list search. So you can actually try it. It's a little slow today. It's probably because it's running on our development server, which is also doing maintenance at the moment. So don't expect great performance. And also we have it on a modest computer in the cloud. The actual ChemAxon database is not at our normal eMolecules site. It's in a cloud server that we just rented for a while. So, but you're welcome to try that if you like and kind of poke around with it. And it won't be available tomorrow, so enjoy it, enjoy it while it's there. And then lastly, this goes to what I said earlier about Andreas being so clever and having to keep up with him. What we've done is we have separated our normal app server from the ChemAxon server via an HTTP REST-based JSON API. As I said just now, this one is actually running, I don't even know where DigitalOcean is, but it's running on a DigitalOcean server. And the eMolecules app server we actually own that hardware. It's in a hosted co-location in San Diego. So it illustrates, the beauty of this is that as time goes by, it doesn't matter, whatever changes take place here on the ChemAxon side, we can immediately take care of them. And it doesn't affect our web application at all because the JSON API insulates us from all that sort of stuff. So to summarize all of this, relational databases are inherently poorly suited to web expectations that have been set by other companies like Google and Bing. And Cheminformatics makes it even worse because of the nature of Cheminformatics. And the solution is twofold. One is partitioning the database for the things we just talked about, and hit lists. This gives you these lightweight queries with instant responses, efficient stateless pagination, and it also gives you power queries with long-running queries that have progress reports and so forth that you can refine and sort merge your results and interrupt and cancel your searches. So the result is a web-capable relational cheminformatics database. Thank you.
So once you have partitioned, couldn't you run the queries in parallel, or is it just not needed because it's fast enough already?
You know, it's funny because some of the guys at eMolecules just asked me that question. Yes, of course you could. One of the things that, as time goes by, if necessary, we can easily run some fraction of those on several different CPUs. The cool thing, though, is I'll say this, that already, if you look at how ChemAxon does this, it's running in parallel already. We have 12 CPUs on that server, and they're all, when you do a query, they're all running. So we're already getting the benefits. In order to scale out more, we'd have to go with more actual computers.
So what is the criteria for partitioning the table from chemistry perspective?
Random.
Just random?
I'm actually considering other strategies. Andreas mentioned the idea of similarity or relevance. One of the things I'm thinking of doing is partitioning by molecular weight. That has the advantage that if you draw a large molecule, you can just start at the partition. You know that the first ones aren't even there. And it also allows you, if you just sort by molecular weight, you tend to get a lot more relevance of the first structures. If you look at what I do, I actually do sort by molecular weight, but that's done as a post step. I pull in all the results and sort them afterwards, not in the database, but in the application. So if I sorted the partitions by molecular weight, I would be able to then do that in the database and save a little bit of trouble in the application end of things.
So for exact search, maybe you can use something like a hash algorithm or something, but that would be very limited.
Well, exact structure searches are easy. You just give it to the Postgres partition, and it sends it out, and you get the answer. You're done. It's really, exact structure searches are no problem at all.
If you use the partitions, that you can also. So is it also works if you want to join with other tables? Is it also very fast?
Yeah, it makes no difference.
Makes no difference. That's
no,
cool.
Postgres handles it all under the covers. It just converts your SQL as needed. So it's the only, it does, there's one, well, I'll talk to you about that later.
Oh, yeah.
But no, theoretically, it just does it for you. If you query the parent table, it just works.
Because in this case, then partition can be, in any reason, very good solution. So
yes.
it's worth to do partitioning of the data.
Well, if you have enough CPUs and stuff, you have to be careful because, like if somebody here mentioned putting them on different CPUs, then Postgres won't handle it. You have to decide how to. You can't combine queries across computers. Yeah. But if you have like, a 48 CPU machine or something like that with lots of memory, it would probably be very effective.
And I guess you heard about Citus?
Sorry?
Citus, that's a solution for using...
I've heard of it, I'm not familiar with it.
We can discuss it later,
okay.
Because probably the others are not interested.
Since rolling out this change, have you seen significant change in like CPU usage or the number of application servers you need? So is there a difference in your
it's not in
Power BI?
It's not in production yet.
Not yet.
It'll be in production probably in a month or two.